Hello! This is going to be a relatively brief, I hope, video to finish off Chapter 9 of Pre-Calculus Made Difficult. We have been discussing how to use trigonometry to find the missing sides or angles of a determined right triangle. One of the most basic applications of trigonometry, both historically and in the present day, has been to use these techniques to measure inaccessible distances. And the classic example that appears in every trigonometry book goes something like this. We have a flagpole, and we'd like to know how tall it is. How can we figure that out without actually climbing the pole? Well, it's very easy with trigonometry, because all you want to do is think of the length we want, the height of that flagpole, as being one side of some right triangle where we have enough information to determine that right triangle. Then SOH CAH TOA should do the rest. Okay, but where's the right triangle? Well, ask a simpler question. Where's a right angle? Once we have a right angle, it's easy to create a right triangle. And of course, the right angle is obvious. Assuming this flagpole was installed correctly, we have a right angle that it makes with the ground. Great. Now to get a right triangle in the picture, let's just start at the base of the flagpole and walk in a straight line for a while. How far? Well, whatever you like. It really doesn't matter. Just be sure that you measure that distance accurately. And unlike measuring the flagpole height directly, which would be very difficult, measuring this distance is a piece of cake. So let's say we walk until we get to this point, and we measure that this distance is, well, let's just say 9 feet. You could go further or shorter, it doesn't matter. So let's just say 9 feet. Anyway, now we have the 3 points of a right triangle. And with the right apparatus, you can make one out of cheap materials, including a protractor. You can measure this so-called angle of inclination from the ground to the top of the flagpole. And that will be whatever it is. For the sake of argument, let's just say it turns out to be 61 degrees. Well, whatever it is, look at what we have accomplished. We have found a right triangle on which we know angle, side, angle. So we have enough information to determine this right triangle. That means we can find all the other parts using trigonometry. And in particular, it means we can find this inaccessible distance, the height of the flagpole. So from here, you could either give it a name, call it X, and pray to SOH CAH TOA, and he will tell you what to do. Namely, he will tell you that since you know this acute angle, and you know the opposite leg and the adjacent leg, you want TOA, tangent. So tangent of 61 degrees is X over 9, which means X is 9 times tangent of 61 degrees, which is about 16.2 feet. Or, even better, you might remember that second SOH CAH TOA shortcut, which tells us that if we have a right triangle where we know an acute angle and a leg of the triangle, not the hypotenuse, then the side opposite the leg is the leg times the tangent of the angle. We could have just immediately looked at this triangle and said this side is, by that second SOH CAH TOA shortcut, 9 tangent of 61 degrees, which is about 16.2 feet. And that's nicer because we didn't have to introduce a symbol, X, we didn't have to set up a ratio or anything like that, but either way will do the job. But I'm going to use this second SOH CAH TOA shortcut later in this video, so it's worth mentioning right here in the beginning. And by the way, when we have this basic setup, what is the hypotenuse? Do you remember that one? I hope so. If not, it turns out to be the given leg times the secant of the angle. And once again, be sure you understand where this comes from if you use it. Very simple. We've discussed that in earlier videos. But the moral of the story here is that we were able to measure this inaccessible distance using trigonometry. Hooray! And there are 1,000,001 such applications, especially anything having to do with surveying. But I wanted to show a sequence of examples, some of which I do in the book, where we apply this idea in a much more interesting setting, namely to astronomy. We take for granted the fact that we can just look up in an instant questions like, how large is the Earth? How far away is the moon? How large is the sun? All sorts of things like this. But where do those things actually come from? It's not like anyone has wrapped a tape measure around the entire Earth, or stood on the surface of the sun to make measurements there. Well, trigonometry is behind all such measurements in one form or another. Just like in our silly little flagpole example, the pole itself may have been inaccessible to us, but nonetheless we were able to measure its height by taking measurements just on the ground. We can do similar things with astronomical measurements. A word of warning at the outset: the kinds of measurements I am going to describe in the examples that follow are beset with all sorts of pragmatic difficulties. Those difficulties are very interesting from a scientific standpoint. point. But that's not my concern right here. My concern right here is just showing how, in principle, we can take measurements that we can make locally and still manage to use them to determine distances that are totally inaccessible to us. And that, I think, is rather amazing. It's one thing to say it's a big world. It's another thing to get a feel for just how large it is. I'm not even concerned with accuracy, so I won't be messing around with significant digits or anything like that. I'm just showing that trigonometry is the right tool for measuring inaccessible distances, even on a cosmic scale. So let's start at home on Earth. We're on a big sphere floating in the void. But how large is that sphere? What is its radius? Oh, by the way, how do we even know it is a sphere? That's a good question. And if this were an astronomy class, we'd probably start there. But it isn't. So I'll leave that for your astronomy professor. Suffice it to say, we've known it is a sphere for a long time, thousands of years. Still, taking this for granted, we return to the question, how large is the sphere? What's its radius? This was the big question in, say, Columbus's day. Columbus was actually convinced that the Earth is much smaller than it really is. And that's why he was sure that he could set off westwards into the Atlantic Ocean, sail around the globe, and reach the Indies from the other side. Well, we know how that turned out. The Earth was considerably larger than he thought it was, and if it had just been water all the way around, he and his men would surely have died. They ran into land, but not the land they thought it was. And the rest is history, quite literally. Now, as for the radius of the Earth, in the book I describe a beautiful calculation done in antiquity by Eratosthenes, an interesting figure himself, in the 3rd century BC. He devised an incredibly clever method for computing the radius of the Earth, and he did it very accurately. That is in the book. I'm going to show you another way, which is more purely trigonometric. Eratosthenes' method is basically geometric. So here's the idea. We're on the Earth. Find a really high mountain, 2 miles high. How can you tell if it's 2 miles high? Well, that's going to involve some trigonometric calculation of inaccessible distances in and of itself. But anyway, we find such a mountain, 2 miles above sea level. Here it is. Obviously not to scale. Now, when we are standing on the mountain peak, we want to look out towards the horizon, a flat horizon, preferably the ocean. So if this is us on top of the 2-mile mountain, we are looking out to the horizon as far as we can see, the point where the land or the ocean seems to meet the sky. So let's just say that point is somewhere here in my picture, and I am staring at it. So that's the furthest bit of land or sea that I can observe from my perch at the top of the mountain. Well, what does that correspond to in my big global picture? Where is the horizon from my perspective up there? Well, you have to imagine if I'm looking down, I can see lots of points on the surface of the Earth. But there are other points, for example these, that obviously I cannot see. The horizon is the furthest point, or the set of furthest points that I can see. Where are those going to occur? Well, it's going to be where my line of sight is actually tangent to the sphere of the Earth. Hey, I like that a lot because I recall a basic theorem from geometry that tells me that if I have a circle and a tangent to the circle, then when I join that point of tangency to the center of the circle, I always get right angles. And where there are right angles, there are right triangles. And where there are right triangles, I can do trigonometry. And where I can do trigonometry, I can measure inaccessible distances. So anyway, let's join that point of tangency, that horizon point, to the center of the circle, giving us a right triangle. And this is good. I've got a right triangle. And R, the thing I'm looking for, the radius of the Earth, is not quite this side of the right triangle, but at least it's in the picture. And in fact, better still, R actually is this other leg of the triangle. Now, just as when we were measuring our flagpole's height, and I said that we could measure that angle of inclination from the ground up to the top of the flagpole, we can do something similar in this situation. Except now, instead of looking up, we're going to be looking down from straight ahead, parallel to the surface of the Earth, down to the horizon that we're looking at. Or equivalently, if we measure that angle of depression as it's sometimes called, once we know that angle, we could get this angle right here, because those two angles add up to a right angle. So this angle is something accessible to us, given the right apparatus to measure it. Well, that angle corresponds to this angle on our global picture, And let's say we measure it, and we find that it is 88.19 degrees. Well, that's pretty good, because I now have enough information in this picture to write down an equation whose only unknown will be r. I just need to relate the hypotenuse, which involves r, this given acute angle, which we know, and the leg opposite the acute angle, which is also r. Well, you could either, once again, pray to SOH CAH TOA, and he'll say, you've got an acute angle. You're interested in the opposite leg and the hypotenuse. So, SOH CAH TOA, use sine. That's fine. Or you could use that first SOH CAH TOA shortcut that I said everybody should know. Namely, if you know the hypotenuse and an acute angle, then the leg opposite the given angle is the hypotenuse times its sine, and the leg adjacent to the given angle is the hypotenuse times its cosine. That should be firmly lodged in everybody's brain. This second one is nice too, but the first one is mandatory. Anyway, using that in this case, we could say my hypotenuse is r plus 2, and I've got this angle. So that means the leg opposite that angle, r, must be the hypotenuse, which is r plus 2, times the sine of the given angle. So times the sine of 88.19 degrees. And here indeed is our equation whose only unknown is r. It does appear in two places though, so we need to pack it into one location. That's fine. All we have to do is distribute over on the right-hand side. Remember, sine of 89.19 degrees, that's just a number, so we can just distribute over that addition, like so. Now we'll gather all the r's on one side, like that, factor out the common r, and of course divide both sides by all this junk, which is just a constant, giving us an expression for r. And when we run that through our calculators, we find that r is about 4,000, and of course we were measuring in miles. And I'm rounding here, just so we end up with a memorable result. The Earth's radius is about 4,000 miles. Remarkable. And we came up with that using only local measurements. The height of a mountain above sea level, and this angle that of course is just measured at a single point at the top of the mountain. Great! So trigonometry can teach us just how large this ball is that we are all sitting on. So Earth's radius is approximately 4,000 miles. And of course, once we know the radius of a circle, we know everything about it. This tells us that the diameter of the Earth, of course, is 8,000 miles. And then how many times does the diameter go into the full circumference? Well, of course, we know that the circumference is pi copies of the diameter. That is basically the definition of pi. It's the ratio of the circumference to the diameter in any circle. So that means in this case, the circumference is about 8,000 pi. 3 copies of 8,000 is 24,000. 0.14 is a little bit bigger than an eighth. So we'd get an eighth of a copy of 8,000 would give us another 1,000. So this is going to be in the neighborhood of 25,000 miles. So maybe I will record this too in our running tally of interesting facts. And so much for the Earth. Let us look up towards the heavens. Let us contemplate the moon in all its ghostly glory. How far away is it from Earth? Clearly it's pretty far away, but how far is far? We can't reach it with our hands. But is it 10 miles away? 10,000 miles away? 10 billion miles away? These wild guesses I'm throwing out are all radically different, but just by staring at the thing, there is no way to tell which one might be closest to the mark. But with some clever experimentation and careful measurement and simple trigonometric calculations, we can get a good feel for how far away the moon is. Suppose this represents the Earth, and this point up here is the moon. I'll label it M, and let the center of the Earth be called E. Now let's suppose that through our careful astronomical records, we know that at a certain time, the moon will be directly overhead a certain point on the surface of the Earth. I will call that point Z for zenith, because if we imagine a person standing there, that person doesn't see himself as standing on a sphere. He sees himself as standing on a plane, which of course would be the tangent plane to the sphere of the Earth at that point. And from his perspective, the moon is directly overhead. He has to look at the highest point in what appears to be the celestial sphere to see the moon. If he were standing somewhere else on the Earth, like say here, then the plane on which he would see himself would be this tangent. And so from his perspective, the moon is definitely not at the zenith. Rather, it's at a certain angle from it. So here, the moon would appear maybe over here. The moon is just there at that moment, but people in different positions on the Earth will see it at different places in the sky. And for some people, such as maybe this guy, the moon will not be visible at all. Not only is it not at the zenith, or at that angle we were looking at before, but from his perspective, the moon is below his horizon. So if he's out there looking up at the stars, he will not see the moon in the sky at all. But anyway, let us suppose that when the moon is directly overhead from the perspective of point Z, we can also find at that same moment in time a point from whose perspective the moon is on the horizon. So that would be something like this point, which I will call H, because if our person is standing there, then from his perspective, when he's looking up at the night sky out in the flat plains, he sees the moon on the horizon. Well, knowing of such a point Z and such a point H is enough, in principle, for us to determine the distance between the Earth and the moon, because this horizon is a tangent to this circle. And of course we know from that fact from geometry that we used already, that means that this tangent is perpendicular to this radius. And where we have right angles, we have right triangles. And where we have right triangles, we can do trigonometry. But what, if anything, do we know about this right triangle? Well, we know one side of it. Side EH is the radius of the Earth. Hey, and we've already found that's about 4,000 miles. But I obviously don't know the other two sides, which should be very close to equal in length, assuming that the moon is very far away from the Earth, so that this little difference is small relative to the vast size of those things. For the purposes of this exercise, let's think of mz as being the distance from the Earth to the moon. But anyway, these lengths are clearly inaccessible to us. So we seem to have just two pieces of information on our right triangle: the right angle and this leg, the radius of the Earth, which we know is about 4,000 miles. And we were lucky to figure that one out without having to burrow to the center of the Earth or anything like that. So how am I going to get a third piece of information on this triangle that will let me determine it completely and therefore figure out these other sides? This angle up here clearly is not something I can reach. And this angle is at the center of the Earth. How am I going to get to that? But we don't have to, because we can recognize that this angle, which we would love to know, takes up a certain fraction of a full rotation. But that's the same fraction, obviously, that this bit of arc length between H and Z takes up of the full circumference of the circle. Aha! So we could set up a little proportion. We could say that angle HEZ, the thing we're looking for, is to a full rotation, that is 360 degrees, as this arc length, arc HZ, is to the full circumference of the Earth. Hey, but we know what that is. That's about 25,000. Well, this is promising because I have 4 terms in my proportion. I know 2 of them. I want this third one. So if I can figure out the fourth one, then I can just push things around and solve for the one I want. And the fourth one is something that in principle I can get because it's a measurement taken on the surface of the Earth, not at the center of the Earth. That is good. So here we would have to turn to our friends, the geographers, and ask them, well, what is the distance between those 2 locations? And they will consult all their vast surveys of the Earth's surface and come back to us and say, yes, we have measured that. And that distance that you seek is, in fact, 6,188 miles. Great. Thank you, geographers. And now we have 3 terms of our proportion, so we can solve for the missing part. And when you do so, you will find that that angle is approximately 89.1 degrees. So let's record that on the figure itself. And now we're in business. On our right triangle, we have angle, side, angle. So the triangle is determined and we can find all its missing parts. We wanted MZ, which is just ME minus a radius of the Earth. So we can immediately observe that by our SOH CAH TOA shortcuts, and it is the more obscure one that applies here, since we know an acute angle and a leg of the triangle, not the hypotenuse. Anyway, using that shortcut, we know that ME is going to be this thing, the hypotenuse. So that will be the leg times the secant of that angle. 4,000 secant 89.1. So MZ, which is what we are seeking, is that stuff minus 4,000, which is the radius EZ that we are subtracting off. And if you run all that through your calculator, you'll find that it is not far from 250,000 miles to the moon from the Earth's surface. An easy figure to remember. So I will record it up here. So considerably further away than 10 miles, nowhere near as far away as 10 million miles. But 250,000 miles is a good ways. Still, it is humbling to think that there are some cars on the road that have driven 250,000 miles. Not many cars, I grant you, but there are some. So if all that time spent driving on long commutes or cross-country trips or whatever it might have been, if all that time had been spent instead on a straight shot on a highway from Earth to the moon, such a car would have arrived. Excellent. And I hope you see that this is really no more difficult than that original problem with the flagpole. It's basically the same thing, at least as far as the trigonometry is concerned. The cleverness comes in the astronomical measurements, with an assist, in this case, from geography. But the trigonometry is just good old-fashioned SOH CAH TOA. Easy stuff. But this shows how powerful it is to measure inaccessible distances by solving determined triangles. Okay, let's keep going. The moon is 250,000 miles away from us. But how big is it? And how can we measure that from Earth without going to the moon and taking measurements there? Well, there are several ways we could do it, but I'll show you one approach that would involve trigonometry. Let's change our perspective a little bit and think of the moon as a circle of some dimensions, because we are, after all, trying to find how big it is. We want to know its radius. And let's think of the Earth as being more like a dot by comparison. Or better yet, let's not have E stand for Earth. Let's have E stand for your eyeball, which of course is very close to the Earth's surface. So here's your eye looking up at the moon. Well, the moon takes up a certain angular distance of your field of vision, some angle like this one. Well, these lines from your eyeball out to the moon that are tangent to it, of course, immediately make us think of this geometric property that we have used twice now. Let us use it a third time and a fourth time. We now have two radii of the moon, each of which is perpendicular to those two tangents we drew just a moment ago. Well, we love this because now we've got the radius of the moon, and that's what we're trying to figure out because we want the size of the moon, and we have a right angle, which means, of course, that we also have an obvious right triangle in the picture. And we know, or can easily obtain, a few parts of this triangle. First of all, it's not hard to measure this full angle that the moon cuts off at your eyeball. And that full angle turns out to be about 1/2 of a degree, which means that if we're just looking at one of these right triangles, that would be about 1/4 of a degree. And we also know the distance from Earth to the moon. Though admittedly, in my picture, there might be a little ambiguity because you might say, well, my eyeball is on the surface of the Earth. Does that mean I'm looking at the distance from point E to this point right here, the nearest point on the moon? Or from point E to the center of the moon, or from point E to the point of tangency? Those are good questions, but they should all give roughly the same answer here. And again, I'm not going for exactitude. I'm just showing in principle how these things could be done. So simply for ease of computation, let's just take that distance to the moon, that 250,000 miles, as being this distance from your eyeball to this point of tangency on the moon. Because if we do that, well, we have angle, side, angle. The right triangle is determined. We know an acute angle and a leg adjacent to it. So that means, once again, I could use this SOH CAH TOA shortcut, and it would tell me that the side opposite my 1/4 degree is going to be 250,000 miles, the leg length, times the tangent of 1/4 degree, which works out, at least as an order of magnitude estimate, to about 1,000 miles. If you stick this in your calculator, you'll see it's actually a little closer to 1,100 miles, but this is something I can remember months and years down the road, whereas I'll forget 1,100. So in the facts that I can carry around in my head, once they've been suitably rounded, I can add that the radius of the moon is about 1,000 miles, which makes it about 1/4 of the radius of Earth. So similarly, it has 1/4 of the diameter of Earth. So if this is the Earth, you could fit 4 moons end to end in a hollowed out Earth. And since the linear dimensions go up by a factor of 4, as we go from the moon to the Earth, that means the area dimensions would go up by a factor of 4 times 4, 16. So the surface area of the Earth would be 16 times the surface area of the moon. And similarly, since the linear dimensions go up by a factor of 4 as we go from moon to Earth, the volume dimensions would go up by 4 times 4 times 4, or 64, which means that the Earth's volume is 64 times the moon's volume. If you hollowed out the Earth and the moon, you could fill up the moon with water or moonshine and pour it into the hollowed out Earth 64 times before it was full. And so much for the moon. Trigonometry has helped us determine how far away it is and how large it is. Similar considerations can lead us to facts about the sun, though of course the sun is much harder to observe than the moon is, unless you want to risk going blind. But with slightly different trigonometric shenanigans, you can discover that the distance to the sun is very large, much larger than the distance to the moon. The moon is 250,000 miles away, but the sun is 93 million miles away, which is actually kind of remarkable because from our perspective on Earth, the sun and the moon appear to be about the same size. They both cut off about half a degree of our visual field. So it might be reasonable to guess, if one knew no better, that they really were about the same size and same distance from Earth. But no, the sun is much, much, much further away than the moon is. Which means, of course, for it to appear the same size from our perspective, the sun must be much, much larger than the moon is. And indeed it is. In fact, we should be able to work out roughly the radius of the sun just by knowing the stuff we have already worked out here. Since the sun and moon appear to be about the same size to us, and the sun is what? 250,000 goes into 93 million. Well, 93 times 4 is 372. So the sun is 372 times further away from us than the moon is, but they appear to be the same size for that balancing act to work out. The sun's radius should also be about 372 times the size of the moon's, so something on the order of 372,000 miles. Actually, I remember when we were doing the radius of the moon calculation, we said this was really more like 1100. So 372 times 1100 would bring us somewhere up in the neighborhood of 400,000 miles. And that is actually quite close. I just looked it up. It's actually about 430,000 miles is the radius of the sun. I'm not going to bother writing that one down because we didn't use any trigonometry to get it, but a good example of just using proportions. Anyway, I want to wrap this video up, but I will mention that it's very interesting to continue this series, and you can do similar sorts of things to figure out the distances to the planets, though variations are required. But the place where it gets interesting jump up in complexity is when you start asking how far away are the nearest stars to us, apart from the sun itself. And the next closest star is very, very, very far away from us. And if you're interested in learning about how those computations are done, they still do boil down to a trigonometric calculation, but they also make use of an important concept in astronomy called stellar parallax. So you might be interested in looking into that and seeing both what it is all about and how trigonometry comes into the computations for the distances to the nearest stars. Once you start talking about stars that are further away, this no longer is useful because the angles involved are so small that they really can't be measured accurately. But there are other techniques, and they can be used to find distances to galaxies and so on and so forth. But at every stage, as we go deeper and deeper into the universe, we still are measuring inaccessible distances, and the main tool for doing that, even in the depths of interstellar space, remains trigonometry. Good night.